Alright, questions about limits usually fall into two types. Either you're asked to show that the limit f exists at a given point AB, or you're asked to show that the limit does not exist at the given point. As it turns out, the methods used to solve these problems are different. Let us first turn to the question of how to show the limit does not exist at a given point AB, let's say. Well, this is based on the observation that if limit does exist at AB, then the limit along every path passing through AB must be the same. So in practice, if we suspect that the limit does not exist, then it is enough for us to check that the limit along certain paths, in fact, 2 will be enough, and show that they are different. Please note that these paths that we choose must pass through the point AB. So formally, this is what the approach says. Suppose the function f approaches a limit L1 as xy approaches AB along path P1, and the function f approaches another limit L2 as xy approaches AB along another path P2, and suppose that L1 and L2 are different, then the limit of this function does not exist. In other words, the function does not have limit at this point AB. Alright, let's see one example. Here we want to show that the following limit does not exist. The function here is given by y over x plus y minus 1. That is our function. And the point in the domain which we are interested in is the point 1, 0. How do we know that the limit does not exist at this point 1, 0? Well, we're going to find two paths along which we'll get different limits. Okay, the first path that I'm going to choose that passes through the point 1, 0 is going to be the x-axis. Right, so this is the path P1 that I'm going to choose, and I'm going to compute the limit of my function along P1 as xy approaches the point 1, 0. So let's see what happens if we compute the limit along P1. Well, the expression for our function can be simplified in this case, since y is always 0 on the path P1. Well, this is not the case in general. If we have points which is off the x-axis, then it is not necessary that y is always 0. However, on the x-axis, which is given by the equation y equals 0, any point xy on P1 will have 0 in the y coordinate. Therefore, when xy approaches 1, 0 on P1, we can always substitute y by 0. Therefore, the limit now becomes 0, the limit of 0 over x plus 0 minus 1. And since y is always 0, then we are left with x approaching 1. In other words, we have reduced the limit of a two-variable functions into a limit of a single variable function of x only. But now the function here is 0 over x plus 0 minus 1, which is just 0. Well, notice that the denominator is never 0 because x is never 1. X is only approaching 1. So x minus 1 is never 0. So 0 over something which is not 0 will always be 0. Therefore, now the limit is limit of 0 as x approaches 1. Well, this is just 0 since 0 is independent of x anyway. Therefore, the limit along P1 is 0. Next, we are going to choose a different path, and hopefully it will give us a different limit. Now, the path that I'm going to choose is the vertical path passing through 1, 0. So there you go. This is the vertical path, which I will call P2, and it passes through 1, 0. Now, because this is a vertical path, it can be easily described by the equation x equals 1. This is because any point on this path will have 1 in the x coordinate. Right, so let's compute the limit of our function along P2. Well, this time the expression of our function can be simplified by substituting x with 1. Because along P2, all our points x, y will have 1 in the x coordinate. So this will simplify to y over 1 plus y minus 1. Now since x is always 1, we are left with y approaching 0. And finally, we have the limit y approaching 0 of the function y over y. Well, we need to simplify this function first before we compute the limit. But after simplification, this is just a constant 1 which is independent of y anyway. Therefore, the limit of a constant 1 is always 1. Okay, so we have arrived at the limit which is different from the one we have previously. Therefore, we have found two paths, P1 and P2 in particular, along which our function has different limits at the point 1, 0. Therefore, there could be no limit in the first place. In other words, the function actually does not have any limit at the point 1, 0. In this example, we are going to show that the following limit of the function xy over x squared plus y squared does not exist at the point 0, 0, which is the origin. As usual, we are going to find two paths along which we'll have different limits. Alright, there seem to be two obvious paths that we can choose to compute the limit. They are the x-axis and the y-axis, since both of them pass through the origin. So let's suppose I take the x-axis to compute a limit as the point approaches the origin along the x-axis. Let me call this path P1, and we know that this is given by the equation y equals 0, since any point on this line will have 0 in the y coordinate. Right, let's compute the limit of our function along P1. Well, in this case, we can always substitute y equals 0 into the expression for a function, and hence this limit can be reduced by writing as the limit of the function x times 0, which is 0, over the denominator, which is now x squared, since y is always 0. This expression is well defined because x is approaching 0 but is never 0. Hence, x squared is some positive number and 0 over x squared is always 0. Therefore, the limit of our function along P1 at the origin is 0. Notice that if we were to choose the y-axis as our path, the limit along the y-axis at this point origin will also be 0 by a similar argument. So I'm not going to give the details here since it's very similar to the one we have here. Instead, I'm going to find another path that hopefully gives us a different limit, or limit different from 0. Okay, the path that I'm going to choose now is the path y equals x. This is a straight line passing through the origin. So let's see what happened to the function along this path as we get closer and closer to the origin. Let me call this path P2 now. So along P2, the limit of our function xy over x squared plus y squared as xy approaches the origin become the limit of, well, since y equals x, on P2 we can choose to substitute y by x. In this case, the numerator will become x squared and the denominator becomes x squared plus x squared, which is 2x squared. So instead of having xy approaching the origin, we can just say that x alone is approaching to 0 because y is now x. Simplifying the function, we'll have limit of half. Since x squared cancel out, we have the limit of half as x tends to 0, and of course this is always half. Hence the limit along P2 of the function as xy tends to the origin is half. So we have shown that the limit of our function along the path P1 given by the equation y equals 0 is 0, whereas the limit along P2 given by the equation y equals x is half. Therefore, we have found two paths along which the function has different limits. Therefore, the limit of this function does not exist at the origin. Alright, in this example, our function is xy squared over x squared plus y to the 4, and we want to show that the limit of this function at the origin does not exist. As usual, we're going to find two paths along which our function approaches different limits as xy approaches the origin. Let us start with the simplest paths we can think of. Well, those are just straight lines passing through the origin, which are given by the equation y equals mx for some real number m. Now, instead of looking at each of these paths individually, why not we just look at the paths collectively by using the equation y equals to mx without actually substituting any specific value for m, and see what happened to our function as xy tends to the origin. Alright, so let us substitute y equals mx into the expression of our function, and this reduces to a single variable function of x only. Moreover, what we want now is the limit of this function of x as x tends to 0. After some trivial simplifications, we arrive at the following limit of the function x times m squared over 1 plus m to the 4 times x squared as x tends to 0. Okay, in the next step, we are going to apply a result in single variable calculus, which says that the limit of a quotient is the quotient of the limit provided this limit exists. So let me write down here the statement of this result, which basically says that the limit of a quotient of two single variable functions, let's say g of x over h of x, and let's say as x tends to some constant a, is equal to the quotient of the limit. So this will be equal to the limit of gx as x tends to a over the limit of hx as x tends to a. Now this is only true provided both the limits at the numerator and in the denominator both exist. Okay, so applying this result in our case, we'll get the following. We have limit of xm squared over the limit of the function 1 plus m to the 4 times x squared. So both of these limits are computed for x approaching 0. Now it's not difficult to see that the limit in the numerator now is 0 and the one in the denominator is just 1. So finally we have 0 over 1, which gives us the answer 0. Alright, before we continue, here's an important remark. The fact that our function approaches the same number 0 as xy approaches the origin along any straight line doesn't say anything at all about the limit of our function at the origin. In other words, up to this point, we just do not have enough evidence for any conclusion. In particular, we cannot say that the limit of our function at the origin exists and is equal to 0. Simply because we have only considered straight lines passing through the origin, and we have not exhausted all the possible paths out there, namely those which are not straight lines. Also, neither can we say that the limit of the function at the origin does not exist, since for this we need to find a path that yields a different limit than 0. So there's still more work to be done, and what we're going to do next is to show that we can find another path different from straight lines that actually gives us a different limit. And from there, we'll be able to conclude that the limit of our function at origin actually does not exist. Alright, the path that we are going to choose is the parabola given by the equation y squared equals x. It's easy to check that this path passes through the origin. In other words, the origin satisfies this equation, and by substituting for x, the function that we have will reduce to a single variable function of y only. In this case, after some simplification, we are actually computing the limit of a constant half, since the term containing y cancel out, so the limit of half is just half. Okay, let us summarize what we have found. Along straight lines given by y equals mx, our function approaches 0 as the point approaches the origin. On the other hand, along the parabola y squared equals x, our function approaches half. Therefore, we have found two paths along which the function approaches different numbers as the point approaches the origin. Hence, the limit of the function at origin does not exist.